in photodiodes, when a photon strikes the depletion region, it creates an electron and hole pair. So you create electrons, you create electrons and holes. Then remember there's a built-in potential within this depletion region. So which way does the electron which way do the electrons go? It should go right, right? It should move to right.
Yeah.
And the holes will move left. So this creates a photocurrent. So by having light, striking the depletion region, you are creating a photocurrent. And one of the most important characteristic of photodiodes is their quantum efficiency. That is their ability to convert photons into charge carriers, including electrons and holes. And this quantum efficiency depends on wavelengths. So for very short wavelengths, that means high or low frequency.
High frequency.
High frequency. Yeah. For very short wavelengths, that means very high frequency. So is the energy high or low? High frequency
High.
and high energy. Yeah. So at a very short wavelengths, photons have very high energy. That means they are very good at generating electrons and holes. So once they reach the semiconductor, they will almost immediately be absorbed by the semiconductor. They will almost immediately be used up at the surface before reaching the depletion region. So it's not a very efficient, at very short wavelengths. And for very long wavelengths, because they have a low frequency, the energy is low, so they are not, sufficient to excite carriers. So this, so that means, the quantum efficiency is optimal in the middle. So we can use photodiodes in two modes. The first one is the photovoltaic mode. That means there's a zero bias, which is essentially here you apply a zero voltage to your photodiodes, then then that means there's a zero dark current. There's a zero dark current. There's no current in dark. Then when there's light, when you increase your light intensity, your photo current will also increase. That's the photovoltaic mode. Then there's also photoconductive mode, which means you apply a reverse bias to your photodiode. By applying a reverse bias, you are increasing your depletion region and reducing the junction capacitance. By having a larger depletion region, there's a higher chance, for your light to reach depletion region. So that means you will be more efficient in generating carriers. So in the reverse bias mode, you will have higher sensitivity because you are more efficiently generating carriers. There will also be higher speed response because you are reducing junction capacitance. So your depletion region is like a parallel plate capacitor. When you increase the distance of the two plates, then you are decreasing the capacitance. So the disadvantage of the reverse bias mode is that there's a high dark current. Even without light, there will still be a baseline current. So when you design your nearest device, you often need to optimize your reverse bias to achieve a better sensitivity here.
In the x-axis, there's just the voltage that's being applied to it.
Yeah, this is the voltage being applied to it. And Y here is your photocurrent.
Okay.
All right. So our photodiodes, generate a current, and we need to convert that into a voltage signal, which is